Welcome to the second learning outcome. This one is all about the practical side, collecting data that genuinely fits your aims and then interpreting it accurately and honestly. The golden rule here is that data collection should serve your research aim, not the other way round. You fix the question first, then choose the sources and methods that can actually answer it. Across this outcome, we build two skills: selecting appropriate sources and gathering relevant data, and then interpreting that data accurately on your own. Good data plus careful interpretation is what turns a topic into real evidence. It's worth being clear on three related terms. An aim is the overall purpose, say, to compare the boot times of 3 operating systems. A research question makes that answerable, like, does a Linux distribution boot faster than Windows 11 on the same laptop? Objectives are the concrete steps: select the machines, run the benchmarks, record, and compare. If a source or a question doesn't help answer the aim, that's your signal to leave it out. When you choose sources, the big split is primary versus secondary. Primary data is what you collect yourself for this project, through questionnaires, interviews, experiments, or benchmarking. Secondary data already exists, gathered by someone else. Things like public datasets, official documentation, and journals. Most student projects sensibly combine the two, setting your own results against published findings. That mix gives you both fresh evidence and a wider context to judge it against. A few pieces of vocabulary will keep everything clear. Primary data is new data you gather firsthand, like your own survey or benchmark results, while secondary data comes from existing datasets, reports, or journals. The population is the whole group you care about, say all first-year computing students, and the sample is the smaller subset you actually study, chosen to represent that population. Getting these terms straight makes your methodology much easier to write. Let's glance at the main primary methods. Questionnaires and surveys gather lots of responses quickly and suit opinions and ratings. Interviews reach fewer people, but give richer, deeper answers about their experience. Experiments and benchmarking measure performance under controlled conditions, and observation lets you watch how users actually behave with a system. The trick is to match the method to the question. Numbers point you to surveys or benchmarks, and depth points you to interviews. Surveys and interviews pull in different directions, and it's worth knowing the trade-off. A survey reaches many people cheaply and gives you mostly quantitative data, numbers, and ratings that are easy to chart, though the answers can be shallow and poor questions will bias them. An interview involves fewer participants and more time each, producing rich qualitative data where you can follow up and ask why. But it's harder to analyze, and the interviewer can nudge the answers. Neither is better outright. It depends on what your question needs. An experiment changes one thing and measures the effect while holding everything else steady. And benchmarking is simply an experiment that measures performance, speed, memory, accuracy, or throughput. You define the variable you change, the independent one, and the variable you measure, the dependent one. So you might change the operating system and measure cold boot time in seconds. The key is controlling everything else: same laptop, same SSD, same dataset, and power settings, so the comparison is genuinely fair. Not every secondary source deserves your trust, so you weigh each one before relying on it. Useful ones include open datasets from places like data.gov.uk and Kaggle, official documentation, and peer-reviewed journals. A handy filter is the CRAP test, checking currency, relevance, authority, accuracy, and purpose. A 2024 IEEE journal article clearly outranks an undated forum post. As a rule, prefer primary documentation and peer-reviewed work over anonymous blogs or AI-generated text. Here's what a good short questionnaire looks like. From a student studying how easy a new timetable app is to use. There's a closed question rating ease of use from 1 to 5. Another timing how quickly people found their timetable. A like it item asking whether the layout was clear. And one open question, what one thing would you improve? For qualitative themes, there's a consent line at the top, and responses are stored anonymously as P1, P2, P3. Notice how neutral the wording is. That's deliberate. This is really about picking the right tool for the job. If you want to compare operating system boot speed, a benchmark experiment gives you quantitative data. If you want to understand why users dislike an app, interviews give you the qualitative depth. To rate satisfaction across 100 users, a survey fits best. And to review known machine learning accuracy results, you'd turn to secondary sources like journals. Each aim naturally points to a method and a type of data. A sample has to represent the population, because a biased sample simply gives you biased findings. Random sampling gives everyone an equal chance and is stronger than convenient sampling, which usually means just your friends, and you want enough responses to be meaningful. A handful won't support a strong claim. Alongside that, manage your data carefully. Label files clearly, back them up, and keep the raw data separate from your analysis. Keeping an anonymized spreadsheet and a note of how each figure was produced will save you later. Once you have numbers, descriptive statistics help you see the patterns. The mean is the average, the median is the middle value, and the mode is the most common one, while the range and standard deviation tell you how spread out the data is. Percentages and frequencies turn raw counts into figures you can compare. Saying, the mean boot time was 22.6 seconds with a standard deviation of 2 across 10 runs is far clearer than listing every raw time. A good chart makes differences jump out that a table might hide. Picture a bar chart comparing the mean boot time of 3 operating systems, with error bars showing the spread across runs, shorter bars meaning more reliable figures. Here, Ubuntu has the lowest mean at 22.6 seconds, and Windows 11 the highest at 38.2. Whatever you plot, always label the axes, the units, and what the error bars actually represent. Let's look at the underlying dataset. Across 10 runs each on the same laptop, Windows 11 averaged 38.2 seconds, Ubuntu 24 averaged 22.6, and macOS 14 came in at 26.1, with standard deviations between 2 and roughly 3 seconds. Every time was measured from power on to desktop on the same SSD and power profile. Holding those conditions constant is exactly what makes the comparison fair. The real skill here is interpreting these results, not just reporting them. Ubuntu booted fastest at 22.6 seconds, around 41% quicker than Windows 11. And the small standard deviations tell us the runs were consistent and reliable. Because the difference is both large and repeatable, it's unlikely to be down to chance. But a fair interpretation notes its limits. This applies to this laptop and these versions, not to every machine. So on this hardware, the Linux distribution booted fastest of the 3. A scatter plot is your friend when you want to see how 2 numerical variables relate. In this one, more installed RAM lines up with shorter app load times, a negative correlation, and a line of best fit summarizes the trend. But here's the catch. Correlation doesn't prove causation. A faster SSD might just happen to sit alongside more RAM in those higher-end machines. So report the pattern honestly and flag any confounding factors that could be driving it. This deserves spelling out, because it's one of the commonest analysis errors. Correlation means two things move together. Causation means one actually brings the other about, and two variables can correlate simply because a third factor drives both. Laptops with more RAM often have faster CPUs and SSDs too, so RAM alone may not be the cause of the speed up. Only a controlled experiment, changing one variable at a time, can support a causal claim. So in your discussion, say is associated with rather than causes, unless your design really proves it. Qualitative data, things like interview transcripts and open survey comments, is analyzed for meaning rather than numbers. The main approach is thematic analysis, which looks for repeated ideas or themes across the responses. You read the data closely, tag the interesting points with codes, then group those codes into themes. You might end up with confusing navigation, slow loading, and liked the dark mode. Braun and Clark set out a widely used 6-step method for doing this rigorously. Those 6 steps give the process real structure. You start by familiarizing yourself, reading everything a few times, then generate codes by tagging meaningful phrases like menu, hard to find. Next, you search for themes by grouping related codes. Review those themes to check they fit and don't overlap, and define and name each one clearly. Finally, you report, writing up the themes with example quotes as evidence. Here's the method in action. 5 students interviewed about a revision app, with their open comments analyzed for themes. Codes like crashes on startup, too many taps, notifications helpful, and good progress tracker start to cluster. 3 themes emerge. Reliability problems, with crashes reported by 3 of the 5. Navigation friction, where people disliked how many taps it took to reach content. And motivation features valued, with the progress tracker and reminders praised. Each theme is backed by a short, anonymized quote, such as P2, saying it kept crashing when I opened it. How you present data is itself an ethical choice. Pick the right visual. Bar charts for comparisons, line charts for trends, tables for exact figures, and label your axes, units, and sample size so a reader can judge the evidence. Never distort a scale or quietly drop an inconvenient result to make a finding look bigger, and state your limitations openly. A small sample, a single machine, one time period. Remember, interpretation means explaining what the numbers mean for your question. So describe, then explain, then qualify. Let's bring the second outcome together. You fix the research question first, then choose the sources and methods that can answer it. Primary data, like surveys, interviews, and benchmarks that you collect, and secondary data, like datasets and journals that already exist, evaluating every source. Quantitative data is summarized with descriptive statistics and shown in clearly labeled tables and charts, while qualitative data is analyzed for themes, often with Braun and Clark's 6 steps. And whatever you find, interpret it accurately. Correlation isn't causation, and every finding is reported honestly with its limitations. That wraps up the second outcome. To take your data skills further, Dawson and Oates are both strong on research methods in computing, and Braun and Clark's paper is essential reading if you're doing any thematic analysis. For sources and datasets, data.gov.uk and Kaggle are great places to practice evaluating and interpreting real data, and cite them right will help you reference them properly. All the ebooks, journals, and datasets for this unit are on Moodle, so make good use of them as you gather and analyze your own evidence.